Hi, and welcome to another lesson in the physics video series. Today, we're going to discuss the PE-KE balance for an object descending under the influence of gravity. In the last lesson, we saw that an object which can be raised to a certain height can then free fall, and the PE and the KE values exchange with each other as potential energy is converted into kinetic energy as the object goes through free fall. In today's lesson, we're going to let this object slide down a ramp rather than free fall straight down. And we're going to see the path independence and the exchange between energy. All right, let's get started. So far, we have established that potential energy is developed when work is invested into an object to lift it from the ground level up to a certain height, and that work is done on this box by the worker when moving against gravity. And when the box moves downward with gravity, work is done by gravity, and the potential energy is converted into kinetic energy. We also determined that the impact speed of free fall was equal to root 2gh. This doesn't just have to be an impact from free fall. We're going to also now demonstrate that this will be the speed of an object as it descends and goes back to the lowest point, which was its starting point. In this inclined plane, we're going to allow the box to slide down the surface until it reaches the lowest point. This is equal over here to the point at which it started with over there. So the only variable that matters here will be the height. As you can see, the V max is the same as the V impact, which is equal to square root of 2gh, derived from setting PE at the top equal to KE at the bottom and canceling m's and solving for V. The square root of 2g times h, which is the height to which the box was raised. This same principle can also be applied to the roller coaster problem, which we will look at in another video. We are now going to do a sample problem for the conversion of energy and analysis with friction loss. Of course, we will include the frictionless situation, and we will add some friction, show you the difference in the final speeds at the bottom of the hill between a frictionless decline and a decline that loses energy due to friction. Let's set up the scenario. Here we have this wedge shape, this triangle, which is the decline. The box has been lifted from the baseline all the way up to a height of 5 meters, and the speed at point A will be 0. We will release this box from rest. The mass of the box is given as 10 kilograms. As the box accelerates down the ramp, it will gain speed. It will also convert potential energy at the top of the hill into kinetic energy at the bottom of the hill. It will pass from A to C, the center line, to B, where the height will be 0. Let's go through this analysis step by step. Step 1. Let's find the potential energy at A and the kinetic energy at A. Well, the potential energy at A is equal to mass of the block times gravity times height, which is equal to 10 kilograms times 9.8 meters per second squared, times that height of 5 meters, which equals 490 joules. So automatically we now know that this system has 490 joules of potential energy stored into it. The kinetic energy at point A equals 1/2 mv squared. But since the V at point A is 0, 1/2 m times 0 squared is still 0. So all of the energy is concentrated in the form of potential with none as kinetic. Now, neglecting friction, we're going to look at the bottom endpoint, B, and we're going to ask what is the potential energy at B and what is the kinetic energy at B as well. PE at B equals mgh. But since the h is 0, 10 times 9.8 meters per second squared times 0, you have 0 joules. And we know from the conservation of energy that the kinetic energy at the bottom is equal to the potential energy at the top. So 490 joules is completely converted. The next question is to determine the potential energy and kinetic energy halfway down the hill. So we can see that the potential energy at C equals mgh. And so 10 kilograms times 9 meters per second times the halfway down the hill, which is 2.5 meters, giving us 245 joules. That is half of the original 490. So the PE had 490 and it reduced to 245, and the PE gave 245 to the kinetic energy, which also has the 245 joules. So PE and KE are equal halfway down the decline. So we know we're dealing with a height of 5 meters, and we want to know how fast will this object be when it reaches point B at the bottom of the decline. We know that setting PE at the top to KE at the bottom, canceling M's and solving for V gives us VB for bottom equals the square root of 2GH. Since it has descended the full 5 meters, we plug in 2 times 9.8 meters per second squared times the 5, giving us 9.9 meters per second. With no friction, falling or sliding down from a height of 5 meters, this box achieves a speed of 9.9 meters per second. Now, if there is friction, it will be less than 9.9 meters per second. Let's take a look at that. In question 5, let's say that there is a 20 joule loss of kinetic energy due to friction. The kinetic energy minus this Q, the 490 joules minus this arbitrary 20 joules, gives us 470 joules. If there is less KE than there was PE, that means you cannot achieve the same speed, nor can you have the same rate of acceleration. Let's take a look at that. In order to find the speed at the bottom of the hill with a friction loss from the kinetic energy, we have to take the kinetic energy formula, KE at the bottom equals 1/2 mv squared. And we solve this for V, giving us root 2KE over M. Now, the KE that we're going to use is going to be the reduced kinetic energy because of a 20 joule loss. 490 minus 20 equals 470. That's the kinetic energy we're going to be using right here. 2 times 470 joules divided by 10 kilograms. That only gives us 9.69 meters. Now you can see very clearly that 9.69 meters per second is in fact slower than the speed at the bottom when there was no friction losses, which was 9.9 meters per second. A problem like this is wonderful for illustrating several points, one of them being the conservation of energy. And another one is how the speed at the bottom of the ramp is less when there is a loss due to friction. So whatever the surface might be, it might be rough, and these two surfaces drag a bit on each other, causing less acceleration and a slower, lower final speed. And that loss of kinetic energy comes out in the form of heat, light, and sound. The work and energy form equivalencies show that the total energy of the system still will remain the same. The potential energy, which is the mgh portion, that depends on the height. The kinetic energy, that depends on the developed speed v. And of course, any of the friction losses in the form of heat, sound, or light would then be added in. But all three together would add always to the total energy ET. As the potential converts to kinetic, and you could see in these bar graphs, the orange bar, which had 490 joules, decreases to 45, then decreases to 0. And while it's decreasing, the kinetic energy bar, which is green, rises from 0 to 245 to 490. So at all times, the green bar plus the orange bar, K plus P, always equals the total energy, in this case 490 joules. When there's friction, the KE bar does not match what it would be when there was no friction. So the potential energy would be decreasing, and instead of the kinetic energy rising to match the exact loss, in our example, we had a 20 joule loss. It would always be 20 joules below what it should have been as it was gaining full energy. So then when you got over here to the bottom of the hill, instead of this being 490, you saw that it was 470. One sure way to test that assertion that the kinetic energy green bar would not rise to the full 490 would really be to take that final speed, which was much less than the frictionless speed, you plug that into the kinetic energy formula, and you don't get the full 490, you actually come up with the 470. So a practical way to do this in a laboratory would be to allow something to slide down a ramp, and you measure its speed, and then you take that speed and you input it into the kinetic energy formula. The energy you have at the bottom certainly will not match the potential energy that you developed at the top. And there you have it. This sample problem demonstrated the PEKE balance without and with friction. And you can see that the path was independent. It does not matter if you fall straight down or you slide on a diagonal. It only matters from the top level to the bottom level. The difference in height between those levels is what's accounted for in the potential energy expression, not the path it took to get to the bottom. I hope you enjoyed this video, and I thank you for watching. I'll see you in the next video where we continue to explore the conservation of energy.